Hi, for our project, we did solving non-separable differential equations using an integrating factor. So firstly, to start, just an overview of simple integration, which we went over in class, shown below. So when we have a differential equation, we solve it by separating the x and y variables and then integrating. So in the example, you can see dy dx is equal to y over x, which then becomes dy over y is equal to dx over x, which then we can integrate, and the final answer becomes y is equal to cx. But sometimes that does not work. So this is one example of that. This equation is not separable.
So let's put this into perspective and look at a real-life example of using non-separable differential equations. Say we have a population of chipmunks, and they're being born strictly at a rate of e to the power of t, where t is time. Their population decreases due to hawk predation at a rate proportional to their current population, as more population would give more visibility to hawks, of course. But as time goes on, they are evolving to eat the hawks instead. So kill rate is modeled by 1 over t times the current population. The chipmunk population growth rate, birth rate minus kill rate, is modeled as so in this very real-life example. dp dt equals e to the power of t minus 1 over t times p. So we know from the previous slides that equations of this form aren't easy, or it's actually not possible to separate the two variables onto different sides of the equation and integrate. So if we want to find p of these little guys, how are we going to do it? Well, we don't give up. Let's look at this in a different arrangement. So if I rearrange it to this form, let's look specifically at the left side. Does this remind you of the derivative of anything? A certain derivative rule? It might have reminded you of the product rule. You can see dp dt plus p, that is reminiscent of the derivative of the product rule right over here, dp dt plus p. So we just have this placeholder function mu, and if we could figure out what mu is, we can take the integral of this whole function, and we can know that it's just mu times p. So how will we be able to figure out mu? Well, let's multiply our original equation by mu, and we can see that it looks very similar, the left side, it looks very similar to the results of the product rule, except for one discrepancy. We can see that mu prime is, instead of mu prime, it's mu times 1 over t. So this is actually very good for us because we can find mu based on this. We can say that mu prime equals mu times 1 over t. So if we do this, and to set it up as a general rule, I'm going to say 1 over t equals a. We can see that if we divide this whole function, this whole equation by mu, we can see that the integral of this would equal the natural log of mu, which would equals the integral of a. And then we can just simply have everything e to the power of this function would equal to mu. And that what we have right here, e to the power of the integral of a, that is the integrating factor. So this is the key concept of all of this. For a function in the form of y prime plus f of x times y, which equals g of x, if you multiply the whole function by e to the power of the integral of f of x, it will set it up to look like the product rule, and then the integral of that side will just be the product of the two functions, the integrating factor times y. So for our function, mu ends up being very simple. E to the power of the integral of 1 over t simply equals e to the power of ln of t, which just equals t. So if you replace mu with t in this equation, we can see that the derivative of this will equal the product. So just taking the integral of this, we have the product of t times p. Then the rest just leaves to solving the right side, which usually we'll be able to solve by either integration at parts or some other thing that we've learned along the way. But the main concept from this is that when you have a differential equation and you can't separate the variables, try to get the function to be in this form: y prime plus f of x times y equals g of x. This way, you can multiply the function by the integrating factor, e to the power of the integral of f of x, to make the left side the derivative of e to the power of f of x times y.
Now let's try another example. So, if the acceleration of an object is shown through this equation, we have to find the velocity function using an integrating factor. So as shown, the first step is moving the 0.196v to the other side of the equation, and then you have to keep both the form and the integrating factor in mind. So the form is y prime plus f of x times y is equal to g of x, or of course that can be substituted with any other variables that we use. And then the integrating factor becomes e to the power of the integral of f of x dx. In this case, that is e to the power of 0.196t. So next, you multiply both sides by the integrating factor, which again is e to the power of 0.196t. And that looks like the answer to the product rule. So with that information, we can now simplify the equation to make it the derivative of e to the power of 0.196t times v is equal to 9.8 times e to the power of 0.196t. So then you can integrate, and remember, every time you integrate, if it's not a definite integral, then there's a constant. So I used k and c as the variables for the constants, and this is the integral that you get. But by subtracting k from c, we just get one constant, so I called the constant from the equation overall c. So lastly, you can either divide both sides by the integrating factor, which is e to the power of 0.196t to get the final equation, or you can multiply both sides by e to the power of negative 0.196t. So your solution for the velocity function is 50 plus ce to the power of negative 0.196t. So, just to recap, solving non-separable differential equations is a really important skill. And just a piece of advice, when you face a problem that seems impossible, explore methods to solve it based on what you've already been taught or what you've already learned. In this case, that was the product rule.